Okay, we'll go ahead and get started here. Test Monday. We'll talk today about what you need to expect, what type of problems and so forth. The test will cover the Think Well material, chapters 2 and 3. And chapter 2 deals with the limits. Chapter 3, we introduce the derivative and the definition there and working through it. So, first off, though, there's 20 problems. And the way I grade these, each problem is worth 5 points. And I check, first off, do you have the correct answer? If so, you get all 5 points. If not, then I go step by step. If you did everything right except one little mistake, you'll get 4 out of the 5. So make sure and show me some work so I can see what your process is. That's more important than just the right answer. So if I just see an answer and it's a wrong answer, then you get 0 points for that problem. But as long as you're showing me something, as long as I can see something you're doing right, you'll get at least 1 point, if not 3 or 4. So, you will be allowed your calculators, but no note cards, notes, no book, nothing like that. No friends, although your friends probably couldn't help you much anyway. Also, I just found out this morning that I have a funeral to go to Monday morning, so someone else will be administering the test for you. But that shouldn't be a problem. That's one of the easier classes to have covered. But the types of problems that we'll be doing will be very similar to the worksheets I've been handing out. We've looked at, well, first of all, the rate of change, average rate of change, kind of working through those slopes of lines through 2 points, and then we kind of later kind of introduced the instantaneous velocity, instantaneous rate of change, slope of the tangent line. But we kind of began with something we already knew how to do and worked our way up that way. So rate of change over an interval, be able to do something like that. Like I said, that would be very similar to find the slope of a line through 2 points. Let's see, then started introducing the idea of limits. And with limits, find the limit, evaluate the limit, in some problems we were given a graph and you're asked to find the limit. And in some cases the graph was a piecewise defined function, and from one side it would go to one number, from another side it went to a different number. So maybe it's one-sided limits. We talked about that a little bit as well. And know the notation for one-sided limits. What does that mean when it's like a plus in the exponent position? That's looking at from the right. So from a graph, you look, well, 3, not exactly at 3, but 3.1, 3.01, what's happening as x gets closer to 3 from the little bit bigger side. And then what's the from the left notation? Looks like a little negative sign in the exponent position. That would be like 2.9, 2.99, and so on. So finding limits, we're going to have several problems of finding limits. Some may be from a graph. Others, we got into a lot of equations, formulas, and evaluating a limit for something that looks like this. Okay. Now, first thing we should do in any of the evaluating limits problems is what? Okay, plug in the x value, see what we get, and in this case we're going to get what? If I pick the problem out of the air correctly, I meant to get a 0 over 0. I think I did right there. When we get 0 over 0, what's that tell us? We got more work to do. Simplifying somehow, manipulating the expression somehow to where we don't get 0 over 0 or infinity over infinity. Okay, so in this case, what we can do, looks like possibly factor the denominator, and well, it actually factors into x plus 1 times another x plus 1. Simplifying this then leaves us with what? That cancels with one of them, and now we're looking at this limit as x approaches -1 of 1 over x plus 1. What happens now as we plug that in? Okay, we get 1 over 0 this time. Well, it's not the 0 over 0, so we're done with the work, but we have to interpret this result correctly. What does this tell us about that limit? Okay, this limit does not exist. And D, N, E is fine. You don't need to write out the words. We're becoming efficient. It's not lazy, it's efficient. Right? Okay. So this limit does not exist. And sometimes once you factor and cancel things out, you may get like 1 over 2 or 3 over 4 or something like that. So that would be the value of the limit. But when we get a number other than 0 in the numerator and then 0 in the denominator, then it does not exist. Okay, questions? Now we saw several other forms of limits where, well, the operations were quite a bit more than just the factoring and canceling what canceled. Some were algebraic limits, limits where we had to multiply things out and simplify. Others, like this one, let's see if I can think of. Well, I don't want. Something like this. Well, first off, what happens when we, well, that's not even what I want. it's not going to let me erase now. How about we do that? Okay, I guess we'll mark that out. Let me change the problem here. Let's just do that in the denominator. Okay. Sometimes when I'm trying to make up problems in my head, it doesn't work the way it's supposed to. Hopefully this will work the way it's supposed to. What do we get here when we plug in 1? Okay. Plug in 1. We'll have 1 minus 1, or 0 in the numerator, and again 0 in the denominator. So that tells us we have more work to do. And in this case we have the complex fraction, as they're called, fractions within fractions. How do we simplify, how do we rewrite this? There's actually a couple different ways to do this, but for a lot of problems like this, the quickest way, most efficient way would be to multiply the top and the bottom by the least common denominator of the secondary fractions, which the only fraction we have within the fraction is this one. So x would be our least common denominator. Okay. So multiply top and bottom by x. And let's see, the top will have 1 minus x. And the bottom, well, in the bottom we don't want to multiply things through. We want to leave it in factored form, so we can simplify or change that form to something we can actually take the limit of. At this point, if we tried to put 1 in for x again, we'd still get 0 over 0. So we still have a little bit of work to do. What can we do to simplify this expression? Now, we don't quite have exactly the same factor in the top and bottom, but we're close. If we factor a negative 1 out of the top, what are we left with then? Okay, we can write that as x minus 1, and there's where we now can cancel our exact factors, top and bottom, and we're left with negative 1 over x. Go back to evaluating the limit, and that limit will equal negative 1. So that's one possible limit process we go through. And one more that's a little bit more difficult, a little stranger looking, involves the square root. Let's take a look at one of those. I'll try to make one up that works. Let's see, we can go. Something like that. Yeah, that works. Plug the 3 in. What do we get? Once again, the 0 over 0, which, as usual, tells us we got more work to do here. Well, what can we do to this one? When we're facing a square root or even 2 square roots like the numerator, we want to multiply by what I call the conjugate. Okay. square root of x plus square root of 3 we have to multiply that top and bottom, and again the bottom we want to leave alone. But what happens in the top? Multiply that out, we get x plus square root of 3 times square root of x minus square root of 3 times square root of x. So those terms cancel out. And then minus, well, square root of 3 times itself will give us 3. So we get x minus 3 left over in the numerator. Denominator, we have, well, our original factor of x minus 3 times the square root factor. And at this point, what do we get? I can cancel our x minus 3's, left with a 1 in the numerator. And then as we plug 3 in this time, for the x value, we'll have 1 over square root of 3 plus square root of 3, which equals what? 1 over 2 square root of 3, and that's fine to leave your answer in that form. Up to this point, you've probably always been told, rationalize the denominator. Well, you can if you want, but I would accept this form. Okay? Questions there? So lots of evaluating limits on our test. We've been doing lots and lots of that over the last several weeks. And again, the one-sided limits, we talked about that. Limits from a graph. Okay. Evaluating functions from a graph, f of 2, for instance, or the limit as x approaches 2. Those may be different values. Okay. And that kind of led us up to a discussion on continuity, whether a function is continuous or discontinuous, or the fancy word discontinuity. Okay. And for a function to be continuous, we have to have 3 conditions. Let's say continuous at, we'll just say x equals c. First of all, f of c is defined. Now, some cases where f of c would be undefined, 1 over the quantity x minus 1, well, x cannot equal 1, we'd end up with 0 in the denominator, so we'd have f of 1 is undefined. Immediately we could say f is discontinuous at x equals 1 because f of 1 is undefined. It's also, these other conditions would not be met either, but number 2 deals with the limit. The limit must exist. Okay. And then finally, the limit value that we found in 2 must be the same as the function value that we found in 1. So if that's not the case, then we have discontinuity at this value of c. Now, some situations, just throw out a couple of examples of graphs that we'd looked at on the worksheets and see why the function would not be continuous at certain values. for this function, where would we have discontinuity? Okay. X equals -1 and at x equals 2. Now at -1, well, first of all, the function exists. The solid dot says f of -1 is going to equal 0. So our first condition is met. Our second condition, the limit as x approaches -1, what can we say about that? Okay, this does not exist because from both sides it's not approaching the same value. Now this we can go back and say, well, what's happening as x approaches -1 from the left? Well, the limit from the left would equal 0. What about the limit from the right of -1? That one-sided limit would equal 3. So from one side it's 0, from the other side it's 3. So it's not the same value. That limit does not exist. And thus we have discontinuity there. Well, what about at x equals 2? Once again, we could say f of 2 exists. This time it's going to be equal to 1. What about the limit? Well, that limit is going to equal -1. From the left side and from the right side, we're approaching the same value. But why would it be discontinuous? These values are not the same. The limit has to equal the function value to make it continuous. Now, there's also two types of discontinuity we talked about. One is non-removable, and the other is removable. Which one of these fits the removable discontinuity?
The one where they reach the limit, but at the points
Okay.
at 1.
Right. The limit exists, so there's just a hole in the graph. Removable means, well, basically the idea is we've taken that one point, we've removed that one point, but everything else fits to where it would be continuous if we put that one point back in the hole. This one at -1 would be called a jump discontinuity or non-removable. It would take much more than just putting one point in place to make it continuous. So you'll be asked to find discontinuities and then to identify which ones are removable and which ones are not. Okay, questions? So chapter 2, lots of time with calculating limits, figuring those out. And then chapter 3, we introduce the idea of the derivative and the actual operation of the derivative. Now we started out looking, again, going back to the rate of change, average rate of change. We did a little bit of that in chapter 2, but rates of change, slopes of lines, slope of tangent line, instantaneous velocity, okay, average velocity, okay, instantaneous or slope of the tangent line those are working directly with the derivative. Average rate of change, average velocity, slope of a line through 2 points, those are kind of working with the slope formula, the other average rates, and those will not involve a limit. But once we start talking about instantaneous and slope of the tangent line, that's where we use the limit definition of the derivative. And in fact, all of those, the limit, well, that limit fits the definition of the derivative. We do that one operation to calculate all those different values. So lots on average and instantaneous rates of change. Now, anytime we have two different points, two different times, or something like that, we'll be dealing with average rate of change. But when we say what is the instantaneous velocity at t equals 1, that's when we have to use that limit. Okay. And we covered a lot of different applications of that. And then we said, okay, find the derivative by the definition of the derivative. And the definition of the derivative looks like this. And there will be some problems where you do have to find the instantaneous velocity, find the derivative, find the slope of the tangent line at a certain point. Sometimes it's better to do it in general, find the derivative in terms of x, then plug in your specific number. Other times you could plug in, if you're looking for instantaneous velocity at t equals 1, you could set this up, and instead of x here and here, you could plug in 1, but you're still going to have the delta x involved in the calculation. But the result of that limit would give you the instantaneous velocity. Whereas, do the formula, you would get maybe 2x plus 3, and then you'd have to plug in your 1 in for the x. So a couple different ways to do some of these problems, but lots and lots of algebra work here. Okay, calculate basically this, and then at the very end do the little bit of calculus with the limit, plug in 0 for delta x, and that gives you your answer. So, and then this last section, we talked about the special functions, derivative of like 1 over x, or the derivative of square root of x. Okay, through this definition, you'll run into calculating the limit of one of those uglier forms where, like we did earlier in the evaluating limits, dealing with the square root, multiply top and bottom by the conjugate, or dealing with the 1 over x. In this form, you'd end up with a complex fraction, 1 over x plus delta x minus 1 over x all over delta x, and from there evaluate that limit. So most of the problems will involve a lot of algebra and just a little bit of calculus. So make sure, hopefully you're brushed up on your algebra skills by now and can work through those. Some of the problems, I will give you like a position function, some of the applications. Some of these last worksheets, you were given the position function and asked something about the velocity, instantaneous velocity at a certain point or something like that. Some problems, the motion of an object worksheet, I also gave you the derivative. So given both the position and the velocity, answer some questions. What's the velocity at a certain point? What's the position at a certain point? One problem on the test may go as far as draw the graph of the motion of an object in horizontal, the horizontal motion. Again, that was wherever our starting point was, and then maybe it went to the right at first, stopped and turned around, something like that. A lot of different applications with that operation, but it's the same operation. Calculate the limit, or in this case, if you're already given the derivative function, make sure you know how to use that in order to describe the motion. So, any questions, any particular problems that we need to go over?